Hi guys, and welcome to today's lesson on composite functions. I really do have to mix up the way I'm opening up these videos. They're all the same. I think I've even got the same pitch. Now, if you are new to my channel, don't worry about it. You are not watching me have an imminent mental breakdown. You are watching me try to say to you, hi, I'm MaffsGuru, welcome, and you're going to watch a video in a moment on composite functions. And you mean, what do you mean on a moment? And I'm going to say to you, do me a favor, can you click that thing over there, that red arrow is pointing to, something along the lines of saying, please support me. Now, what that'll do is subscribe you to my YouTube channel and the other 8 people in the world who are currently watching these videos. Yes, nobody wants to watch maths videos, do they? Why do I want you to subscribe? Just so I know you're out there watching. I mean, it might well be that I'm just sitting in here in a room talking to myself. Who knows? But if you are watching and could click that, it would make life so much better for me. I get all excited when I get a new subscriber. It's quite sad, really. Put out a YouTube or put out a Facebook or a Snapchat, and trust me, I will be deliriously weird for hours. Anyway, enough of that. You want to know what a composite function is? Well, so do I. Lol, I already know what a composite function is. Don't worry about it. By the end of this video, as you can see above, we are going to do the learning, which is going to be what a composite function is, how to find GOF and FOG. Now, fog is basically that misty stuff that no, it's nothing to do with the weather or a bad horror movie. Well, we'll come back to that. How to know if a composite function is defined, how to then create that composite function algebraically, and how to find the domain of said composite function. There's a lot in this. Now, we've recapped pretty much a lot of the lessons that we've gone before. Now, I've recorded about 4 or 5 videos so far, which is the opening of this course. And if you're going to understand what a function is, what a domain and a range is, the idea of a one-to-one function, a many-to-one function, what makes a function, in fact, will probably help with all of these lessons. But today we're going to concentrate more on what a function is and how to find the domain and range and sort of work those all in together. Now, one of the great ways I put this together for my students last year when I did this was come up with something that was real world. Now, if you're out there in the UK or India or America or any other country that's watching these, do me a favour, have a party pie. They're fabulous. In the UK, I know it's a bit weird. We have like fat, massive pies. They have itty bitty dinky pies filled with meat. Put them in your mouth, squodge of barbecue sauce, and you are in heaven forever. I know, weird, huh? But the point of this lesson, again, I'm not having a mental breakdown, I promise, is I want you to imagine that we have a cow, and I'm going to put it through some sort of process, just see what I did there, processor, anyway, and out comes some mince. So I've taken something, I've put it into a black box, a mincer or something, and out has come mince. And then I've taken that mince, and I've put it in through another process. This could be baking or whatever else. And in this situation, my picture says I've put it in pastry. And out has come a beautiful party pie. You're going to say, what on earth are you talking about? Well, actually, this is what this lesson deals with. It's the idea of, if I take a function and put it through some sort of process, I'll get an output. If I can take that output and put it into a different function, and it comes out with some sort of result, then that is a composite function. And you're going to say, what are you talking about? I know, chill. But you remember these input-output machines? I don't know whether you had them. In the UK, we did them a lot, and it was all very exciting. So we did a little boxy thing and a times 2, and said, give me a number, and we said 6, and we had an output that was 12, and it all got, anyway, a whole new discussion. But that's very much what we're sort of going to deal with. And we call them here composite functions. Now, let's go back to this idea about input and output. I just talked about it a minute ago with these input-output machines. But I want you to now start thinking about domains and range of functions. Every single part of this course, I promise you, deals with a graph. It might deal with trig functions, sines, cosines, and tangents. It might deal with straight lines or polynomials or cubics, which a cubic is a polynomial. Anyway, a whole new discussion. It might deal with graphs of x squareds or graphs of the root of x or all sorts of things. And you have to know what these graphs look like. So the one I've just highlighted there is 3x plus 4. What would be the domain of that? Now, just as a recap, domain is any x value that can go into that from minus infinity to infinity. So is there any value that cannot go into 3x plus 4? Is there any value that I can't multiply by 3 and add 4 to? And the fact is, no. So my domain for that function is real. What about my range? Okay, well, my range is what values would be created as a result of putting my x values in. Now, because this is a straight line that effectively has a gradient of 3 and an intercept of 0, 4, careful, it's not 4, then actually we also know that my range is real. There are no values on the y-axis that wouldn't be created by putting in an infinite number of values from minus infinity to plus infinity, anyway, in my function. So the domain and range for that function is both real. What about the graph of y equals x squared? Now, notice I put g of x equals x squared. Why can I call it f of x? Well, what we're going to deal with in a moment is taking one function and plonking it into another and seeing what happens and what comes out. So if we've defined f of x as 3x plus 4, we can't then go on and create f of x as x squared. So we can call it g of x or h of x or whatever letters we use. But generally speaking in maths, we use f, g, and h. So again, what is the domain for my graph of y equals x squared? Well, this becomes easier if I can see what that looks like. And I know the graph of y equals x squared is a parabola. And I know that it's in fact valid for all values from minus infinity to infinity. So my domain is real, but my range is not. Why? Well, if you think of my standard y equals x squared curve, does it have any value that goes below the x-axis? And the answer to that is no, because if we draw a very quick sketch, there is my graph of y equals x squared. So we now know the range is r plus or 0. Now remember, it can't be and 0. You can't have 1 and 0 coexist. It's just not possible. It has to be or, union of. So finding domains and ranges are actually going to become critically important. But what we're now saying is, if we wanted the output of g of x to be placed into f of x, we can write it in two different ways. This is where we get to this fog and goff stuff, trust me. And the notation in maths is important. You're going to say, why would I want to put them inside each other? Chill. So this is one way of doing it, where we say a new function, and they've defined it of h as x, is equal to the function of g of x. Now go back to what that means. Normally we would have something like f of x equals 3x plus 2. And you'll notice that that x there and that x there are the same. The reason being is we're saying we're having some sort of function that is related to the value of x, my unknown. If I am trying to put g of x into my function, then rather than writing f of x, I'm now saying, well, I want that x to disappear because I'm going to put my value of g of x into my whole function. You're going to say, well, why would I do that? Well, just chill for a second. I keep saying that, no, chill. Another way of being able to write this, and again, Barry, hashtag no more Barry. Barry has been added again because what he's trying to do is say, well, there should be a shorter way of doing it, so a sort of shortcut. And what they do is they come up with this f o of g. Now what that means is that g is being placed into f, all right? So it's the composite of f and g, or g is being placed into f. And that's what composite functions are. I'm taking one function and putting them into another. Now obviously we could also have GOF, to go back to what was at the beginning of this lesson. And GOF just means that I'm taking f, I'm putting it into g. So let's see, what would h of x be if that were the case? So actually let's do it with the algebra here. So if we had the f of g of x. So my f of x was 3x plus 4. I'm taking that x now and making it g of x. And so that says do 3 times my g of x, which is x squared plus 4. And there we go. That is the composite of those two functions. And what about if I wanted to do g o f? Could we do it? Well, algebraically, absolutely, because what that means is now I want the g of the f of x. So we are now saying we want the f of x all squared, because remember my original function for g of x was x squared. So I'm now going to say my function of x was equal to, he says, trying to bring it back, 3x plus 4. So we have 3x plus 4 all squared. Now algebraically, putting those into each other isn't particularly complicated, but we need to know whether these functions are actually going to exist. And I'll talk about what that means in just a second. But I asked the question here in red, would FOG be the same as GOF? And what we can see is there is FOG, there is GOF. Are they the same? No. And the big thing about composite functions is 99.936% of the time, I made that up, literally made that up, they will not be the same. Okay, so don't assume that they are. Very, very important. Now, I said here about the idea about whether composite functions are defined or possible. In my previous video, we looked at the idea that when we actually did sums and products and take subtraction of ordinates or different functions together, they were only defined when there was an overlap. Very similar here for composite functions. We have to make sure, so if I have my function of x here and I have g of x here, whatever I put into here and get out of here, we have to make sure that my output, my range of my f of x, can totally fit within the domain of my g of x. If not, we're going to end up putting some dodgy values in and my g of x is not going to be able to cope. All right, so all of my range of f of x has to fit within the domain of g of x, or it's just not going to work. I can't put an undefined value into my g of x because it just doesn't exist. It's just not possible. So we have to make sure that these things are possible. Now, here's an example from the Cambridge Essentials textbook, which is the textbook series I am using to teach this course. And what it says is, for the function g of x, so I'm going to write g of x is equal to 2x minus 1, and we've got f of x is equal to the root of x. Now, my brain, the second I see these, is saying, right, I need to know a quick sketch of what these are going to look like. Well, I know that that's a standard function. There's my root x, and I've already got started thinking about domains and ranges. And this is 2x minus 1, which is effectively just a straight line that goes through minus 1. All right, okay, so now my brain's thinking about domains and ranges. And that's the whole trick to here, because we need to make sure that the range of one function fits into the domain of the other. I need to find the domain and the range of each of these functions. So the domain of that would be all real, and in fact the range of that would all real, which is great. Straight lines will do exactly that for me. Now let's do the same for the next function. So my domain, or let's write it dom and ren, I don't know why. Oh, my domain. Now, because my square root graph starts at 0 and goes on to infinity and beyond, I can write this in a number of different ways. I could write it as r plus or 0, and likewise with my range, r plus or 0. Alternatively, some people like to write that in interval notation by writing, because we're going to include 0. They can also write that the domain is equal to 0 to infinity, and my range would also be equal to 0 to infinity. All right, no one way is right or wrong. It's down to personal preference or what the exam tells you to do. Now, the trick to be able to then work out the rest of this question is to sort of put a table together. And I, again, extracted this from the Cambridge Essentials textbook series. And what you'll notice is they've got domain and range on the top and my two functions at the bottom. Okay, so let's now start asking the questions. State which of FOG and GOF is defined. Now, for it to be defined, the range of the first function must fit fully within the domain of the second function. Okay, so that's important. So if I now look at FOG, we're putting G into F. So I need to make sure that the range of G is contained within the domain of F. Okay, so that all of my range is fitted into the domain. So let me see. So my range of G, which is real, does that fit into the domain of that? For it to be defined, absolutely everything from my output of my range must fit into the domain. And what we can see here is that while my range is all real values, my domain of my F is actually only defined by real plus or 0. Yes, so the point of it is that my negative values are going to spit out of my G function and go into my F function. They're not going to go anywhere, and as such it is not defined. If that's the case, if values come out of my range and have nowhere to go in as my domain, then it is not defined. What about GOF? So in this situation, I need to know, does my range of F fit within my domain of G? So rubbing this out to make it a bit clearer for myself, does my range of F, so my range of F, does that fit within my domain of Gene? Gene? Who's Gene? G. Yes, it does, because all positive real values and 0 fits within my real value. So everything that comes out of my function of F is going to fit within G, and so we now say that GOF is domain. See how easy this stuff is when you understand the principle. For the composite function that is defined, state the domain and the rule. Okay, so we had that g of x was equal to, sorry about the scrolling, I just need to try and remember 2x minus 1. And we knew that f of x was equal to the square root of x, although that now looks like a 3. So we now know that g of f is defined, so that means I've got the g of the f of x, which gives me, so I'm going to take 2, and I'm going to put f of x everywhere I see an x, so 2 f of x minus 1, which gives me 2 the square root of x of minus 1. And ladies and gentlemen, there we go. That is the rule for my composite function. What else did it say? And the domain. Now, one of the important things to notice is that when we have the domain of g of f and it is defined, then the domain of that function is exactly the same as the domain of f. And if you think about it, why? Because the values that are going into f are creating the range that comes out, and that range fits wholly within the domain of g. And so the domain of my whole function must equal the domain of what my original function was. And so the domain of this function, all right, the domain of g of f is equal to the domain of f. And what was the domain of f? Well, if we just check again, the domain of f was r plus or 0. Now that was a fairly rudimentary example. We're going to get a bit more complicated with this one here. For the function f of x equals x squared minus 1 and g of x equals the square root of x. It looks very similar, doesn't it? But it's not, I promise you. State why g of f is not defined. Okay, so we're going to give a reason why it's not defined. So first thing we're going to do is I'm going to do my domain, create my table and range, and I'm going to have f and I'm going to have g. All right, sorry about my handwriting, ladies and gentlemen. We'll try and tidy it up a little bit. So what is my f function? My f function is a parabola. Oh, but it's a parabola that has been shifted down by 1. All right, so it has, there's minus 1. I know that's minus 1, and I know that's 1. Don't worry about why I put that, but it's important. So I now know that my domain is all possible r values. And what about my range of that function? Well, my range is going to be from minus 1 all the way up to infinity. So I'm going to put minus 1 to infinity. And I'm going to use interval notation in this particular instance. All right, what about g of x, my domain of g? Well, what is my function of g? It is the square root of x again. Notice how often these come up. So I know that my domain is going to be 0 to infinity, and my range is going to be 0 to, that doesn't look like an infinity, that looks like a theta. Come on, Darren, put it together. Okay, so I now have my domains and ranges for all those functions. State why g of f is not defined. So we have g of f, which means I'm putting f into g. So my range of f must be fully contained within my domain of g. So my range of f is minus 1 to infinity, and my domain of g is 0 to infinity. And as you can see, that is not contained within. Now that's perfect notation. I can actually put that and say, well, because minus 1 to infinity is not contained within 0 to infinity, therefore g of f is not defined. And I would write that, therefore g of f not defined. All right, you can write it in a whole sentence, but I'm cautious this video is going to be long. Right, okay, so now they're going to ramp up the pressure a little bit. They're going to say, right, define a restriction of f star. Sorry, define a restriction f star of f. So what they're now saying is we're going to restrict that original function. So we're going to look at this function here, because this was f of x. And we're going to say, right, how can we restrict that function such that g of f or g of f star will be defined? Oh, okay then. So if we now look here, the reason that this didn't work was because basically we needed the output of our function to provide me with values from 0 to infinity. Yes, so again, we wanted the output, the range of my function, which is coming from minus 1 to infinity, but we needed that to go in and become 0 to infinity. So we've got to get rid of basically this minus 1 to 0. Well, how do we do that? Well, to be able to stop this section of my graph from appearing, then what I can say is f star colon is going to be all real values except from -1 to 1 mapped onto real of f star of x is equal to x squared minus 1. Now what that is saying to me is we will have all real values of that original function, but not anything between -1 and 1. And funny enough, you can absolutely do that. This is freaking awesome. All I've done is I've just gone, do you know what? Let's just ignore a bit of the function. Yeah, we don't want it. It's fine. But drawing this sketch was actually really important to me. And I can't impress upon you all. Draw the sketches. It will make life so much easier with these type of things. All right? And then it says, and find G, O, F star. Now, funnily enough, the F star is irrelevant because all this is now telling me is do G of F star of X, which means I'm just going to say G, which was the square root of X, but where I now see an X, I'm going to put F star of X. All right, so that becomes f star of x was still x squared minus 1. Oop, hello-ness. Still was x squared minus 1. And I'm just going to put a square root under it or over it. And ladies and gentlemen, there is my defined function. I suppose we should also work out what the domain of G, O, F star is. And if you remember the domain of that, it would be equal to the domain of f star of x. Which gives me, what was the domain of f star of x was all real, but not anything between -1, whoops, and +1. Ladies and gentlemen, I am nearing the end of this lesson, I promise you, but if you are looking at GOF, you've got to make sure the range of f is contained within the domain of G, right? Or the range, whatever comes out of f, wholly fits into the domain of G, or it's not defined. We can't have any dodgy values come out. Likewise, if we're looking at FOG, make sure that the range of G fits wholly into the range of f. And as I say, in most cases, FOG does not equal GOF. Ladies and gentlemen, there is no recap in this one at all because I am done. Thank you so much for watching. Hopefully that made sense. Hopefully the examples sort of helped you realize. And my cow and my mincer and my party pie couldn't have got any better. Oh, I'm now hungry. Ladies and gentlemen, it's been good. Thank you so much. If you can, send out the word on Instagram, Snapchat, Facebook, and wherever it is to say, hi guys, there's a pretty interesting channel here led by a slightly bizarre English guy. If you haven't already subscribed, there is a doohickey there for you to subscribe. Thank you so much for taking the time, if you could. And if you haven't, wow, you're a tough audience. Otherwise, there's a video over there loading for you of a similar nature. Thank you very much. Have an awesome day. I'll look forward to seeing you again. MaffsGuru, out.